Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up section 6.4, which was seeing an application of definite integration to physics, which is through the concept of work. In the previous video, we took a sort of look at the basic sort of work formula that with constant force and over a distance d, you can measure the work by doing force times distance. And then we looked at sort of two extensions of that formula in situations where certain pieces of whatever you're sort of moving need to travel different distances, which we sort of term the changing distance situation. And then we also saw what to do when the force, or in our case, because we're just sort of always focusing on lifting things, we looked at a second case where you have a changing force or a changing weight. In other words, the object that you're moving, you're lifting it all the way to one point, but along that sort of path or along that journey, the weight of that object changes. So we did a couple examples that sort of tied those together. In this video, we're going to look at one more example of that just to make sure that we're still comfortable with those concepts, and then look at a slight extension of an example where instead of having multiple pieces, where in one piece maybe the distance is changing and in the other piece the sort of weight or force is changing, an example that puts those together simultaneously. So we'll have a couple more examples with this, and then we'll be finished with this application of definite integration here. So, for this one, we're going to first begin by supposing that there's a well with a 100-foot chain that weighs 150 pounds. Attached at the bottom is a leaky bucket that weighs 1 pound, so the bucket itself weighs 1 pound, and currently contains 10 pounds of water. So you lift this bucket up at a speed of 1 foot per second, but the water leaks out at a rate of 0.2 pounds per second. That's why we would call it a leaky bucket, because it's leaking out water over time. We want to determine the work necessary to lift the bucket, rope, and water out of the well. I guess that should say chain there, but again, it doesn't really matter. So, one thing that's not explained in this section is why we are constantly interested in lifting chains, ropes, water, wells, all this sort of stuff, but that's sort of besides the point. It's a nice example of what we're trying to sort of do here. So, let's begin by first taking a look at sort of a diagram and understanding the different pieces here. So, if we draw ourselves our sort of diagram, there's our sort of well there. We know that the overall distance is 100 feet. We know that we have this sort of chain component, which we know the sort of chain weighs 150 pounds. Then at the bottom, we have this sort of bucket, which we're viewing as sort of a point. The bucket is 1 pound bucket, and then we also have 10 pounds of water. And then of course we also know that we are lifting this thing up at a rate of 1 foot per second, but the water weight is decreasing at 0.2 pounds per second. So, as we know from our sort of previous example, we're going to have to try to divide this into several different pieces and then sort of combine all the work together. So we can sort of see that the work overall should be able to be measured by the work to lift the bucket. That should be very easy because the bucket is always 1 pound and it has to go all the way to the top. And then we will add to that the work of the chain, I guess. So if we can do this chain component, which will be a little bit trickier because each sort of segment of the chain, if you will, needs to travel a different distance. And then at the end, we will add the work of the water. And of course, the work of the water, the challenge there is that it initially weighs 10 pounds, but as it's going up, the weight is going to decrease, so it's going to be less work than we would think. I mean, if the 10 pounds had to just travel all the way to the top, then 10 pounds times that 100 feet would give us about 1,000 feet-pounds of work, but we know it's going to be less than that because that water is going to get lighter and lighter as we lift it up. So we'll need to do each of these three components. Now, the bucket component, we don't need an integral to do that. We should be able to just do that manually. The work for the bucket is going to be that 1 pound times the 100 feet. So we should immediately be able to get that that is going to be 100 feet-pound. So the work for the bucket, nice and easy. It is a constant weight traveling the entire distance. All right, now let's go ahead and work on that chain component. So again, we'll sort of redraw and just focus on the chain. So we'll ignore the water, we'll ignore the bucket, just focus on the chain component. So there's this sort of chain component. We'll orient ourselves. Again, doesn't matter which way, but we got to have a consistent orientation. So we will do the same as we did in the previous problem. We'll call the top x equals 100, and we'll call the bottom x equals 1. Sorry, the top x equals 0 and the bottom x equals 100. Now we'll sort of imagine we're going to take an arbitrary piece at xi star, and then what we will do is we will cut on the two sides of that a section of chain that is with delta x. So we're taking a piece of chain that is delta x, so a segment of the chain, and then we are going to lift that segment of chain all the way up to the top. So we should be pretty comfortable what this is going to look like. So the work for this segment of chain is going to be equal. Well, we need to know the weight of the segment of this chain. Well, this segment of chain is delta x in length out of the fact that it is 100 feet overall. So we can expect that the force is going to be delta x over 100 times the overall weight, which is 150. So that'll be its force there, because as a portion is delta x over 100. So if that delta x is 1, then it's 1/100th of the overall chain. If the delta x is, say, 2 feet, then it's 1/50th of the chain, so on and so forth, right? Whatever delta x is, delta x over 100 tells us what proportion of the chain it is. The overall chain weighs 150 pounds, so this will tell us the weight of that piece. How far does the piece need to travel? Well, it needs to go from here up to there. So that's from x equals 0 to x equals xi star. So we'll have xi star there. That means that the overall work, or what we were calling, W chain, is going to be roughly, again, this is just an approximation, the sum over those xi star of, I guess we can simplify this a little bit. Looks like we should get 1.5 xi star delta x. Then we can change this into an equality by taking the limit as delta x goes to 0. So we're basically saying, instead of actually having this be a full segment, let's sort of smush this together until it's infinitesimally thin. So just taking an infinitesimally thin slice of chain and lifting it all the way up. Of that xi star, 1.5 xi star delta x. And then we get that this can be a definite integral. These xi stars can be chosen anywhere from x equals 0 to x equals 100. So we have bounds of integration, 0 to 100, 1.5 x dx. Integrating that is not so bad. We get that that's 0.75 x squared, evaluated from 0 to 100. I suppose we can plug that in, and looks like the W chain here is going to be 7,500, right? Because we multiply this by 100, and it'll go 1, 2, and then multiply by 100 again. So it would be 7,500 feet-pound. So does this make sense in sort of an estimation sense? Well, if all of that weight of the chain was at the very bottom, then we'd have 150 pounds that would need to travel 100 feet, which would give us 15,000 feet-pounds. That's a massive overestimate because, of course, the chain's weight is not all at the bottom. So our answer, 7,500, makes sense because that's halfway. That's sort of imagining that the weight is actually all directly in the middle. So 150 pounds needing to travel 50 feet would give us that 7,500 feet-pound. Of course, this is how we want to view it because we want to view it as an integral. So there we go. We've got our work for our chain. So we've got the work for the bucket, work for the chain. Now we're ready to go ahead and look at the water. So let's give ourselves another page and redraw the stuff that is relevant to analyzing the water situation here. So we'll go ahead and redraw. There's our well. We still have this orientation to stay consistent. So there's x equals 0. There's x equals 100. we know that the water down at the bottom was initially 10 pounds. So this is 10 pounds of water. Last time we found it useful to think about these sort of as ordered pairs. So at x equals 100, then the water weight is 10. What else do we know? Well, we know that the actual thing is being lifted up at 1 foot per second. So 1 foot per second. And then the water weight is decreasing at 0.2 pounds per second, if we remember correctly. Yep. Okay. So, what we'd like to do is we'd like to figure out a formula that tells us if we pick any arbitrary spot, what the water weighs at that moment. So again, we're sort of taking a little arbitrary moment here, xi star, and we're sort of imagining the water is right there, and then we're going to take it just a delta x step forward. So we're going to take it from xi star and then move it another delta x. So what we want to try to calculate is the work necessary to move that delta x. So we need to figure out a force and a distance. Now, of course, the force component is going to be tricky because that's going to be based on the weight. So we need to figure that out. But the distance component should be very easy. We're just moving it delta x. So it's going to be times that delta x there. So we need to figure out the weight at any particular moment. Well, last time we used the sort of speed to figure out what it was going to weigh at the top. So if we think about this, if it's moving at 1 feet per second, right, and we have 100 feet, so 100 feet divided by 1 foot per second tells us it takes 100 seconds to reach the top. And if it's losing 0.2 pounds per second, then by the time it goes up 100 seconds, well, minus 0.2 pounds per second times 100 seconds, that's going to be negative 20 pounds. So it's going to lose 20 pounds of water by the time it reaches the top. Now, we should be very hesitant there because we only had 10 pounds of water to start with. Meaning if we lost 20 pounds, this up here should be like negative 10 pounds of water. That doesn't make any sense. So what that actually tells us is this tells us this is too much. So the bucket must empty at some point. So at some point, all of the water leaks out before we actually reach the top. In other words, this is a very futile situation. We're going to do all this work, and by the time we actually get the bucket to the top and we'll have lifted the whole chain, we'll have lifted the bucket, there won't be any water in there. So we know that it must empty out at some point. So we need to figure out, where does it empty? So where does it empty in terms of x? Well, that shouldn't be too hard to figure out, right? We know that you're losing 0.2 pounds per second, and in 100 seconds you lost 20 pounds. We only had 10 pounds to start, so that must mean that in 50 seconds it's going to empty out. So it will empty after 50 seconds. Well, 50 seconds, and since we're traveling 1 foot per second, means that it'll empty when x is 50. So it will empty at x equals 50. So the other moment that we should be interested in is when x is 50, the water is equal to 0. So what does this mean in terms of our integral? Well, our integral is only going to make sense from here to here. What sort of linear model is going to make sense with these? Well, we can still set up our sort of equation, our sort of water weight model. It's supposed to go between these 2 points, 50, 0, and 100, 10. So we can come up with the slope. Slope is going to be 10 minus 0 over 100 minus 50. Which looks like it's going to be 10 over 50, so 1/5. And then, of course, unfortunately, neither of these is the y-intercept, so we'll have to manually sort of solve for that. So we can get that the water weight is equal to 1/5 xi star plus whatever the intercept is. We'll need to sort of plug in one of these. So maybe we'll just plug in this one, 50 and 0. So we get 0 equals 1/5 times 50 plus b. And looks like we should get negative 10 is equal to b. That negative 10 is not a surprise, right? Negative 10 would be if we continued the same pattern all the way up to where x is 0, we expected negative 10 pounds of water to be left. So our model makes sense there. All right, so we now know that the sort of water weight is equal to 1/5 xi star minus 10. So we can go take this thing here and plug that in to our force formula right there. So we got 1/5 xi star minus 10. Again, you might be a little confused about why this is a positive slope when the water is running out. It's again because we're focusing downwards this way. So notice that as x is larger, right? If x is 50, the water is only weighing 0 pounds. When x is 100, it's weighing 10. So the larger x is, the more the water weighs because our axis is facing downwards. So there we go. That's the work necessary to move the water at any xi forward by just delta x. So that tells us now how to figure out the overall work. So our our work for our water overall is going to be approximately the sum over all the xi stars of these expressions, 1/5 xi star minus 10 delta x. We can change it into an actual equality by taking the limit as delta x goes to 0 of this summation. Notice that this part always is going to pretty much run exactly the same, right? So once we actually have the expression, it shouldn't be hard to convert it into an integral. Then that tells us that w for the water is actually the definite integral. What sort of x values make sense? It's not 0 to 100 because this water only makes sense from 50 to 100. So we'd have the integral from 50 to 100, 1/5 x minus 10 dx. And there we go. There's our work for our water. Now if we actually calculate that, the work for the water is 1/10 x squared minus 10x, evaluated from 50 to 100. If we plug in 100 into there, looks like we should get, well, we can just calculate it. The work for the water is going to be 100 squared, which I guess is 10,000 divided by 10, which is 1,000. So 1,000 minus 1,000 minus, plug in the 50, so that's going to be 2,500, so 250 minus 500. Looks like, sorry to have to squeeze this in, the work for the water is equal to 250. So, and that would be, again, in our pound feet, or our foot pound. So I think you usually write it the other way. Not that it really matters. Okay, foot pound. There we go. So there's our work for our water. Now, might be a little confused about why the work is still positive. Well, if you think about it, when you're lifting it up down here at the beginning, you're doing work, right? The water still weighs something, right? At the beginning, the water is pretty heavy. So even though the water runs out by the top, in other words, you don't get any water in the bucket by the time you lift it up, all from here to here, you're doing work to lift that water. And that amount of work is that 250 foot-pound. Does that make sense? Yeah, I mean, we're taking our 10 pounds of water, and obviously not all of it makes it up even to this point, but even if all this 10 pounds did make it up to this point, then that would be traveling 50 feet. 50 times that 10 pounds is 500 pounds. We know that not all that 10 pounds makes it, so our answer of 250, which is a bit less than 500, makes sense. So what's our overall answer? Well, we can go back. We've got our bucket is 100. We had that the rope was 75, or the chain was 7,500, and we got 250 here. So we can say that the overall work is that 100. It was 100 feet-pounds plus the 7,500 feet-pound plus the 250 feet-pound. So that looks like it's going to come out as 7,850 feet-pound of work overall to lift that chain, the bucket, and the water. Even though you're only lifting the water for the first half of the trip, it does contribute work, and ultimately you do all of this work, and all you end up with is a chain and an empty bucket. Okay, so usually to most people, the most challenging part of doing this is, well, twofold. One, understanding the difference in how we're sort of measuring these things. Keep in mind, just like we mentioned in the previous video, when we're working with the chain or the rope, the delta X represents sort of a length. It's a segment of the chain that we are lifting completely to the top. Whereas here, we are actually using the delta X as a measurement of how far we're going to move. We're going to take whatever water we currently have and move it just a little bit by delta X. Another thing that a lot of times people who have a little bit of trouble with is making sure you understand this linear model here. This linear model is basically saying that we want to know at any X value along the way, what is the current amount of water. In this case, we automatically knew how much water there was at the bottom. We normally like to know how much water there is on the top, but in this case, that didn't make sense. So instead, we found the moment where it ran out, and then we constructed a linear model that goes through those 2 points. We're going to do one more example, stopping though with wells and buckets and things like that. That'll also involve building a linear model that'll help us understand this a little bit further. So let's get to one more example of calculating work through integrals. All right. So what we're going to do here is we're going to look at another sort of situation that is a very basic sort of work situation. In this situation, what we're going to be doing is we're going to be pumping water or liquid out of some sort of container, which you can basically think about as lifting that liquid out of the container. So we have the following container that you have a diagram of here. It is made up of a cut cone. So basically this is a cone, but that's been chopped off here and here. We're told that the top radius, so the radius up here, is 4 feet, and the bottom radius is 8 feet. We know that the height of the container is 6 feet, so there we go, there's our 6 feet. We also know that the container is completely full of water, so the entire container is full of water. Water, we're told, has a density of 62.5 pounds per cubic foot. We're going to suppose that there is a spout at the very top of the container. We're going to determine the work necessary to pump all the water out of the container. So in other words, we're going to, if you want, so you can basically say lift all the water up out this spout. So the water down here has to travel all the way up there. The water here has to travel to there. The water here has to travel to there, etc. Now, this example is sort of a culmination of all the stuff that you guys have learned so far about work, because this is an example where both the distance and the weight will be changing. What do I mean by that? Well, if you want, take for just a moment to think about this thing sort of metaphorically. Imagine sort of slices of water and actually just lifting them. Down here, the slices need to basically travel the full 6 feet. Whereas here, a slice is only going to need to travel a couple feet. Furthermore, a slice down here has a larger radius, meaning it is a bigger slice, meaning it is heavier. So down here, we have heavier pieces that need to travel further. Whereas here we have lighter pieces that don't need to travel as far. So this is going to combine what we've studied so far in terms of both a changing distance and a changing weight or force. So let's go ahead, redraw this diagram, and give ourselves sort of an oriented axis here. So there we go. I'm going to sort of just redraw my cut cone quickly. Okay. There we go. We know that the spout is at the very top. We're going to give ourselves an axis. We're going to orient down just like we've been doing. I guess we could call that x equals 0 then, and we could call this x equals 6 here, because we know that if it's 6 feet, the bottom's going to be at x equals 6. We also have this radius component. We know that down here the radius is 8, and here we know that the radius is 4. I'm going to also record that over here. When x is 0, the radius is 4, and when x is 6, the radius is 8. Notice that this looks like the setup that we were just doing with lifting the water, because we can sort of build a linear model that tells us about the radius, which is changing at any moment in terms of x. All right. Next thing we're going to do is we're going to imagine picking a random piece, xi star. We're going to give our slice a little bit of width. So we're going to give that delta x, and we're going to imagine cutting into our shape there. The little piece that is with delta x. Okay, so we're going to cut out this piece. So let's cut that out. And notice that what this is basically cutting out is approximately it's approximately a cylinder. Now, why is it approximately a cylinder? Well, notice I drew my line straight here. But, of course, we know that actually it would be a little bit angled. But, again, we're going to at some point make that delta x really small. So it won't really matter if there's a slight angle here. We can say it's approximately the same as a cylinder there. All right, what we're going to then try to do is we're going to try to figure out the work necessary to lift that cylinder or that piece all the way up to the top. So our goal is to try to figure out the work to move this piece to the top. Well, as we know, that's going to be the force for that piece or the weight of that piece times the distance. Let's think about the distance first because that should be a little bit easier. The distance, well, the distance is different depending on where we pick. We're choosing xi star and we're going up to x equals 0. The distance between those is that xi star. So the distance here is simply going to be xi star. So that'll be our distance. If we choose xi star down here, then this will be larger. If we choose xi star up here, it'll be smaller. So that should make sense. What about the force? Well, the force of that piece is going to be equal to the weight of that piece. Well, how would we figure out the weight of the piece? Well, we have the density, which tells us how much it weighs per cubic feet. And remember, per cubic feet means in terms of its volume. We know how to figure out the volume of this, and we can multiply that by the density to get the weight. So the force of this piece should be 62.5 times the volume of the piece. What is the volume of a cylindrical piece? Well, it's 62.5 pi r squared h. Because how do you figure out the volume of a cylinder? You do pi r squared, that's the area of a circle, times the height. All right, well, we need to know the radius and the height. Well, what is the height of this thing? Well, it's how tall this thing is, which is exactly that delta x. So that h is going to be equal to delta x. What about the r? Well, the r changes. At the top, it's 4, and at the bottom, it's 8. So we can come up with a model for the radius based on our xi. So this will be a model here. Let's go ahead and figure out what that model should look like. Okay, so what should that model look like? Well, it needs to go between these points of 0, 4, and 6, 8. So it goes between 0, 4, 6, 8. So we can get the slope, m equals 8 minus 4 over 6 minus 0, which looks like we get 4 over 6, which would be 2/3. Positive slope, let's make sure that that makes sense. If you're looking down this way, notice that the radius is getting wider, right? If you're looking down the container, then the radius is widening. So it makes sense that we have a positive slope there. Then we can say the radius is 2/3 x plus the intercept. Got to find this intercept, but notice we can just plug in this guy, that's 0, 4. Gives us 4 equals 2/3 x, 2/3 times 0 plus b, which tells us 4 equals b. So this tells us our model is that the radius here is equal to 2/3 x plus 4. So if you pick an x value somewhere between 0 and 6, you can use this formula, 2/3 times x plus 4, to tell the radius. And you can check, if you want on your own, that at x equals 0, you do get a radius of 4, and if you plug in x equals 6, you do get a radius of 8. So our model makes sense there. So we can put all this stuff together. Let's give ourselves a new page here. So we said back from here that the overall sort of force of this piece is equal to this. Let's just grab this real quick. Okay, So there we go, where we've got our sort of piece there. We also figured out that the height had to be delta x, and we just figured out that the radius can be written as 2/3 xi star plus 4. So if we plug that in, we get that the force for this particular piece is 62.5 times pi times 2/3 xi star plus 4 squared times delta x. So we now have the force. We came back over here. We also already had the distance, so we can get the work for this single piece. All right, so the work for this piece then has to be this 62.5 pi, 2/3 xi star plus 4 squared delta x times that xi star. All right. Let's go ahead then, and actually this is the work for the piece, so the overall work is going to be approximately the sum over the xi star selections of this thing, 62.5 pi, 2/3 xi star plus 4 squared delta x xi star. This is an approximation. Why is it an approximation? Well, we did make that sort of loose assumption that this thing, which has a slight slope to its edge, can just be viewed as a cylinder, so that is only an approximation. But, of course, it's not going to be a concern once we take the limit, so we can say equals the limit as delta x goes to 0 of the sum xi star 62.5 pi 2/3 xi star plus 4 squared xi star delta x. I'm just putting the delta x at the end because that's where we traditionally see it when we're doing a Riemann sum. This indeed is a Riemann sum, so we can say that the work is the integral. Where does it make sense to choose these xi stars? Well, we had to do this since the tank was completely full from x equals 0 to x equals 6. So our bounds here, 0 to 6, 62.5 pi, 2/3 x plus 4, again, no longer need to make individual selections, we're doing it for all x, squared times x times dx. So there we go. There's an integral for the work to lift all the water out of this container. I'm going to skip going ahead and evaluating this because, again, I think we've done enough evaluations and I'm more interested in setting up the integral. But before we sort of wrap up this example, I want to just, again, sort of point out where these pieces came from. This is definitely a more complicated example, so let's just recap real quick. So, first of all, thing that we have to sort of recognize is what we're imagining is we are moving slices of this water up to the top, one at a time. We know that slices at the bottom were going to be larger, heavier, and have to travel further, whereas slices closer to the top didn't have as far to travel and were actually smaller and lighter. To sort of measure those slices, what we did is we cut out these things that were approximately cylinder shaped. Then we said, let's try to figure out the work necessary to lift that slice or chunk of water to the top. That needed to be the force or the weight of that piece times the distance. The distance was very easy. It was just our choice of xi star. If xi star is down here, well, then we're measuring from 0 to there. If xi star is here, we're measuring from 0 to there. So the distance was just xi star. The force or the weight of the piece was much harder because this was based on the fact that we had water, which has density 62.5 times 62.5 pounds per cubic foot. To figure out the cubic feet, we needed to know the volume. That's why having a cylinder was nice, because the volume of a cylinder is pi r squared h. For this pi r squared h, the h was easy, because that's the height of the cylinder is just this width of the slice, which was our delta x, but the r was more challenging. Why was r challenging? Because it changes. If we're near the top at x equals 0, the radius is smaller. If we're near the bottom at x equals 6, the radius is larger. So we built a model that goes through those 2 points, 0, 4, and 6, 8. We built a linear model, mx plus b, because as you guys can see, I mean, clearly that's a linear relationship going along the edge. We found the slope, we found the intercept, and we built our model. Once we had our model, we plugged that into our equation. Then, once we had the force or weight of the piece, we multiplied that with the distance, created an approximation by summing them up, changed that into an actual equality by taking the limit, and then converted that into a definite integral. If you guys want, you can try evaluating this one here. It's not particularly hard, though. You do have to do a little bit of messy stuff with foiling that out. Otherwise, it's all good. To wrap this up, though, what I'd like to do is look at how, if we change some features of this question, what the overall resulting integral and how it would be impacted here. So we're not going to do any more computations, but I'd like to just look at a couple situations and see how they would impact this integral. So this example continued. We're going to rewrite, but again, not evaluate the integral for the work necessary to pump the water out of the container with the following modifications. So we're going to do 3 separate modifications. Each time we're going to sort of reset and just do one modification at a time. So just to sort of recap what we had. So remember that in our initial case, just to rewrite everything we just did, I mean, not all the work, but just the sort of result. In the initial case, we had this cut cone shape. That's a pretty horrendously ugly looking cut cone. There we go. Okay. This thing, remember, was 6 feet. The top had a radius of 4 feet. The bottom had a radius of 8 feet. The spout was directly on top, and it was completely full of water. And we found out that the work could be measured as the integral from 0 to 6, 62.5 pi, 2/3 x plus 4 squared x dx. That was ultimately the integral that we built there. All right, so let's think about A. A says that the water is only 2 feet deep in the container. So we have the same container. There we go. Okay, 4 feet up top, 8 feet here, still 6 feet here, but now the water is only 2 feet tall. All right, so what we want to try to do is, without having to redo everything, let's think about what this would impact in terms of our integral. So if we think about our integral, right, if we think about these components, let's think about the bounds first. Where did the bounds come from? Well, the bounds came from choosing those xi slices. So here we said we could choose a slice of water down here, we could choose a slice of water here, we could choose a slice of water near the top, so on and so forth. Is that going to change here? Well, absolutely, because you're not going to choose any slices of water here because it's not full there. So we'd only be choosing down here. Remember that our perspective was this way here. So from our perspective, if this is x equals 0 and this is x equals 6, well, the water starts at x equals 4. Again, that's a little bit weird. It doesn't start at x equals 2, but that's because we're facing downwards. So what should be our new bounds? Well, it should be the integral from 4 to 6, 62.5 pi, 2/3 x plus 4 squared x dx. So the difference here is that we would change the bounds, and that's simply because the water only makes sense from that x equals 4 down to that x equals 6. All right, the spout is an additional 1 foot above the container. So for B, we're going to reset, so we're going to assume that it's full again. So we're going to say it's back to the same container. Still 4 feet. Still 8 feet. Still 6 feet. Back to being completely full. But the spout is up here, so you have an additional 1 foot. Well, what is this going to impact? Well, again, let's work our way across. So, integral, we can still choose slices from up here all the way down. So, our bounds are still going to make sense to be 0 to 6, because remember, we have the top at x equals 0 and our bottom at x equals 6. The 62.5, well, that's not going to change. That was based on this density of the water. The pi, that just came from the cylinder. The 2/3 x plus 4, that came from the relationship about how the radius was changing. And the x. Well, what was the x from? Well, remember, the x was from the distance it needs to travel. And that's going to change here. Because now, if you think about it, if you pick anywhere from 0 to 6, well, if you choose that x value, you got to travel to 0, and then you got to travel an additional foot. So we would now be able to just change that to x plus 1 dx. So this would now handle the work. If the spout was an additional foot, we would always have to go 1 foot extra in terms of the distance. All right, lastly, we're going to sort of reset everything. So we have our container, same container. Again, there we go. X equals 0, x equals 6. We're going to be back to having the spout at the top, but we're going to imagine that it has a liquid inside of it that is only 20 pounds per cubic foot. So, shouldn't be a surprise what that's going to change. Whatever this liquid is, it makes sense to slice it from x equals 0 to x equals 6, so we'd have the bounds 0 to 6. We're not going to have 62.5 there anymore because we've changed the density. We'll have 20 pi. Still going to have the same relation here, so it's still going to be that 2/3 x plus 4 squared. And since we're just going back up to here, no additional distance up to like a spout for that for some reason sitting above everything else, we'll be back to x dx. So the reason I wanted to do these follow-ups is to show you guys that if you understand the structure of what we're doing, these types of sort of related questions don't need to have everything built from scratch again. I really want you guys to sort of understand that each component in the sort of integral is relating to a different feature of the sort of container. You'll notice that one feature that did not change was this 2/3 x plus 4 in each of the equations. That's because that was based on the actual design of the container. The only way that that 2/3 x plus 4 would change is if we literally gave ourselves a different container for the problem. If we had a different upper radius, lower radius, and height, then that formula in there could change. So that pretty much does it for the section 6.4 on work in your textbook. Remember that there are a couple other work situations that are covered in the textbook, specifically Hooke's law. Since we didn't talk about those in these lecture videos, those are not part of what you guys are responsible for in terms of section 6.4. So when looking over 6.4, you should basically only focus on the situations of lifting these sort of rope, bucket, chain, water type situations, or pumping sort of water or some sort of liquid out of a container. Those are the only two situations we're considering for our course. In the next video, we'll move on to another, and actually for a while, the last application of definite integrals by talking about average value.